All right. So let's resume our session with my cat right here. So there may be background noise when she is scratching. All right, sorry about that. Um, so why virtual memory, right? So basically, I think to understand virtual memory, you will want to make sure that you are aware that for most of the thing that you do in your program, if not all, every single data access, whenever you see an address, those are virtual memory, and that's a good reason on why. All right. So first of all, you think about ideal memory, right? An ideal memory, you want something to be unlimited, right? You also want to have the virtual view of your own memory. Basically, if you write a program, you want to be writing a program with the assumption that whatever you do, whatever memory you get, these are your own, and that's it. No one else is using the memory, right? Because otherwise, basically, let's say you look at your computer right now, there are like 10 different applications running in the background or foreground, to be honest, right? Each with its own memory usage. The programmer, let's say you're programming your own program, I should not have to worry about where the other process data are, unless you're working with things like embedded processor, which is a totally different thing, right? But imagine, let's say you want to initialize a big array, an array that consists of 10,000 elements, right? You want to make sure that the 10,000 elements actually from your perspective are next to each other, that are next to each other. But in reality, they might not be next to each other. Virtual memory give you that illusion. And you also want to have memory protection, which means that, let's say I have multiple applications running, right? One application should not be able to access another application's data because that's kind of violate privacy, right? Uh, and the user also should not be able to read or write kernel's data as well. So what exactly is the virtual memory, right? So basically the way you would envision this is, think of it as the simplest form of virtual memory system that I would tell you is, think of it as a function that takes in your virtual address and give you the physical address. So what is a virtual address? Virtual address are the address that the programs use and see. Basically, let's say you program in C or C++, right? Those addresses are virtual address. Physical address are the location, if you will, the location in DRAM. Where should the data be in DRAM? And virtual memory system is basically treated as a function, right? That takes in the virtual address and will give you the physical address. This allows the program to basically use the address assigned to the program, and it essentially will give the physical location of your data. Each process also has its own view of their memory address. This address is called the virtual address, right? And the function that translates, basically the unit that is used to translate the virtual address to a physical address, is called the memory management unit, or the MMU. It performs the mapping, it then translates for you. All right. So with that in mind, right? How can you actually have unlimited memory? This is like the one of the goal of virtual memory. I mean, with modern day computer, we have a lot of DRAM, so it's not much of a problem anymore, but still it is a feature given to you by the virtual memory. So technically this is limited, but there are ways to create this illusion, because you think about this, right? You have DRAM. And then you also have the hard drive, right? So if you can detect, for example, any data that you rarely use at all, like for the past 10 hours, maybe you should kick them to the hard drive, because you're not going to access them in the next 10 minutes, likely, right? And then you keep the frequently used data in the main memory. So that's how you can get the unlimited memory. So that's the second benefit of virtual memory on top of just having this address protection. Also things like illusion of contiguous memories. I can map my virtual address to a much bigger space in hard drive, right? Using, well, two things, the page table structure and the OS, right? Page table structure plus the OS, which allow you to kind of like tell where the data is going to be. And then one more concept is a page, right? A page similar to a cache block. The virtual memory system also keep track of things at the different granularity, and the granularity that they track things are in a page granularity. Think of it as it's just a size, some size, right? It's a range of addresses. Typically, is 4 kilobytes. Like basically, most modern OS would treat one page as 4 kilobytes, but it can be bigger or smaller. Okay, it can be bigger in many like keys. Like for example, the GPU would have a page size much bigger than 4 kilobytes, for example. All right. And then you also have this page table. I would compare this to like a what's the game is called? Like a treasure hunt game or scavenger game, right? Where you given a clue, the clue will give you the location of the first location, it will give you the next clue, which will give you the next clue, which will give you the next clue until you finally get to the treasure or the goal, right? So the way virtual memory system works, kind of like that through the page table, right? Before we go there, think of it this way. A page, right? Let's say you look at DRAM. You basically would then divide your DRAM into multiple pages, right? So each of these boxes is like 4 kilobytes. 4 kilobytes, right? And let's say in your program here, right? Your program need to use maybe 12 gigabytes of data, right? So it's 12, not 12 kilobytes of data. These would span 3 virtual pages, right? So these 3 virtual pages, right? The way the virtual memory system works is there'll be a mapping for each of these 4 kilobyte virtual pages to some of these 4 kilobyte physical pages. It can be anywhere, right? So you think this 12 gigabyte as a contiguous large chunk of data. In reality, some of this page might be over here at the top, some of this page will be at the bottom of your DRAM, and that doesn't matter. It's okay because we can then access the page, right? Translate this in Thai just to make sure everyone understands on the same page. Okay, no pun intended. ก็คือให้คิดว่าเราแบ่งแรมเป็นก้อนละ4กิโลไบต์แต่ก้อนนี้เราจะเรียกว่าเพจนะครับไอ้เพจเนี่ยมันจะเป็นก้อนขนาด4กิโลไบต์แล้วโปรแกรมเราสมมุติเราต้องการที่ขนาด12กิโลไบต์ใช่ไหม12กิโลไบต์เป็นขนาดกี่เพจครับทุกคนต้นจ้านอย่าเอาของไปเรียนมั่วสิลูก12กิโลไบต์เป็น3เพจเนาะเพราะว่าเพจหนึ่งมัน4กิโลไบต์ไอ้3เพจเนี้ยมันจะไปแมปตรงไหนก็ได้ในแรมซึ่งไอ้ mapping ตรงเนี้ย virtual memory system เป็นคนจัดการก็คือเรามี virtual page มาก้อนหนึ่งมันก็จะแมปไปที่ physical page ตรงนี้ขึ้นอยู่กับการแมปของ virtual memory นะครับมีคำถามหรือเปล่าคำถามตอนนี้ก่อนถ้าไม่มีเดี๋ยวเราไปต่อกันนะครับ so with this model right I would say the next question would be all right I know that we want to do the mapping the question would be how do I do the mapping all right because we somehow we need to maintain all this mapping you would then, if you read textbook on architecture or computer system, where you and you dive into the chapter on virtual memory, there'll be this thing called the page table, right? You can think of it as a large table that store basically the location of the page, even the virtual page. I mean, again, think of it this way. It's a big table that given the virtual page, you get the physical page out of it, right? And it can be used to determine the physical page. So the page tables will be a hierarchy of a bunch of levels in a tree-like structure, right? And all the tables are stored in the memory. Again, the page table will be in the memory. So in the Intel 86 64-bit machine, there are 4 levels. If it's a 32-bit machine, it's 2 levels of this, where you have the root for each of the process. The root will be assigned and point to the first level. Okay, you would then use the virtual address plus the data from the first structure to go to the second level. All right, let me translate this in Thai ก็คือวิธีการทำงานของไอ้ page table แล้วก็การทำเขาเรียกว่า virtual address translation เนาะก็คือแปลงจาก virtual address เป็น physical address อะมันจะทำงานนี้มันจะเอา virtual address ออกมาดูแล้ว virtual address อะมันก็จะมีเป็น address ใช่ไหมมันก็จะมี information ให้เราดูว่าเฮ้ยจาก address เนี้ยต้องวิ่งไปตรงไหนก่อนเหมือนเวลาเราเล่นเกมหาสมบัติก็คือเรามีคำใบ้แรก virtual address จะเป็นคำใบ้แรกของเราคำใบ้แรกมันจะบอกว่าสมบัติอยู่ตรงไหนแต่ว่ามันต้องไปที่โลเคชันอันที่1ก่อน page table ตัวแรก page table ตัวแรกบวกกับคำใบ้แรกเราจะได้คำใบ้ที่2มาว่าโลเคชันที่2ที่ต้องไปอยู่ตรงไหนโลเคชันที่2ก็จะเป็น page table อันที่2แล้วอย่างใน 64-bit processor ของ Intel เนี้ยมันจะมี4 location ก็คือต้องไป4 รอบก่อนที่เราจะรู้ว่า data เราอยู่ตรงไหนนะครับ and in the page table right, what you store is called the page table entry and that behave like a tag if you will right that provide information on where the next page table is located the whole process is called page walk basically this is going through multiple level of page table structure to figure out your physical address. So let's do some quick example with a 32-bit machine. So we'll do 2 levels first of page table. Each page table contains 1024 entries, right? So that's the 32-bit Intel 86. In this system, usually address 32 bits. 1000 entry doesn't mean it's going to take 1 kilobyte of memory because it depends on the size of the page table entry. In the Intel processor, this 1000 entry, each entry is 4 bytes, so it's basically combined to one single page, 4 kilobytes. Given some random virtual address, right? I can ask you, what would be my physical address? And here's one example. Because your address is 32 bits, your page size, right? Page size is 4 kilobytes, right? So I know that within the page, everything will be organized the same way. So the last part of my address will be telling me what byte in the page am I trying to access. We call this bits, the page offset. The size of this is the log2 of page size, which is essentially, if it's 4 kilobytes, this is 12 bits, right? So the last 12 bits is used for the page offset. The other 20 bits, you have 20 bits left, right? Each one of these have to be used to access the table for 2 levels. So I can subdivide them into 10 bits and 10 bits. The way this page walk work is essentially, right? You now have the first table. You know the root tells you the location of the first table, so this is known. You then take the bits here. So let's say these bits are 0, 0, 0, 0, 0, 0, 0, 0, 1, 1. So that's 10 bits, all right? So let's say those are a bunch of 0 followed by 1, 1. That's number 3. If you convert this binary to decimal number is 3, right? So the way this actually work is I would go to the fourth entry that correspond to number 3, right? So it starts from 0, 1, 2, 3. So you go to that table. It has 2 information. First and the second information. This is a status bit to say this would be checking is access legal. Okay, basically check if this is an okay access. PTE3 will contain the location. Basically, this would give you the location of the next table. It tell you, hey, go there, that's your next table. When you have the location of your next table, you then look into this part, and let's say this number is 0, 0, 0, 0, 0, 0, 0, 1, 0, 0. What's this number in decimal? This is number 4, right? So you would then use the number to index into the second level, which will now point you to this entry, right? This, because that's the last level, we call the number, whatever go here, we call this a physical page number. You take this part, you add the page offset, and that becomes your physical address. All right, so I'll explain this again in Thai just to make sure. Basically, ก็คือเราจะมี address ของเราเป็น address ในโปรแกรม เราจะแบ่งส่วนบิตล่างสุดก่อน เป็น page offset page offset มีหน้าที่อะไร page offset เนี่ย มันจะชี้ไปที่ byte ที่เราต้องการ access ในแต่ละ page สมมุติเราต้องการ access byte ที่ 25 page offset ก็จะมีค่าเท่ากับ 25 เลย แล้วก็มันจะชี้ไปที่ว่า เฮ้ย จาก byte ที่ 0 น่ะ วิ่งไปที่ byte ที่ 25 นะ แล้วนั่นก็คือ data ที่เราต้องการ access แล้วใน page offset เนี่ย ใน physical page กับ virtual page มันจะหน้าตาเหมือนกัน เพราะฉะนั้นมันจะเป็นพาร์ทที่แบบแชร์กันระหว่าง virtual address กับ physical address อันนี้มันจะเหมือนกันแน่ๆนะครับ ขนาดของ page offset ต้องมีกี่บิต สมมุติว่าเราสามารถวิ่งไปที่ทุก byte ใน address space เราได้ page offset ก็จะมีขนาด log 2 ของ page size page size ก็คือ4 กิโลไบต์ เพราะฉะนั้น page offset อันนี้ก็จะเป็น12 บิต จากที่ผมตีต่างผมบอกว่า page server มีขนาด 1,000 entry 1,000 entry ใช้ 10 บิตในการวิ่งเข้าไป access เพราะว่า 10 บิตเนี่ยมันพอที่จะ cover ตัวเลข 0 1,023 นะครับ 1,023 entry ก็คือ 1,000 entry 1,023 ขอโทษนะครับ ผมผิดนี่1,023 นะครับ มันจบที่ 1,023 ทุกคน ไม่ใช่ 1,024 นะครับ เราจะแบ่งเป็น10 บน 10 บิตบนกับ10 บิตล่างนะครับ 10 บิตบนเนี่ยก็คือบิตที่ 31 ถึงบิตที่ 22 ตัวเลขเป็นอะไร มันจะบอกเลยว่าเราต้องวิ่งไปที่ entry แถวไหน ถ้าสมมุติตัวเลขนี้เป็น 20 เราก็วิ่งไปที่แถวที่ตัวเลข 20 ถ้าเป็น 0 วิ่งไปที่แถวที่ 0 แถวแรกนะครับ ถ้าตัวเลขเป็น 1,001 เนี่ยก็วิ่งไปที่แถวที่มันเป็นเลข 1001 ในแถวนั้นมันจะมีข้อมูลให้เรา2 อย่าง อย่างแรกคือข้อมูลที่ชี้ว่า table อันต่อไปอยู่ตรงไหน อันที่ 2 เป็น status bit ดูว่า access เนี้ยมัน legit หรือเปล่า บางทีเราเผลอไปใช้ access เพื่อนเลยอะไรเงี้ยมันก็จะ set false นะครับถ้าเป็น access ที่ legit มันก็จะชี้ว่าtable อันที่ 2 อยู่ตรงไหน table อันที่ 2 มันก็จะหน้าตาเหมือน table อันคล้ายๆกับมันมี 1,000 แถวเหมือนกันนะครับ แล้วเราจะใช้อีกพาร์ทหนึ่งใน address ที่ผมเขียนว่า level 2 index bit เนี่ยก็คืออีก 10 บิตที่เหลือเอามาใช้บอกว่าเราต้องวิ่งไปแถวไหนใน table อันที่ 2 เพื่อ access data เราสมมุติเราตัวเลขนั้นคือ 4 ก็วิ่งไปที่ช่องเบอร์ 4 ช่องเบอร์ 4 ในนั้นจะมี information ให้เรา 2 อันเหมือนกัน อันแรกเป็น status bit ก็คือ access นี้มัน legit หรือเปล่าพาร์ทที่ 2 เนี่ยเขาจะเรียกว่าอันนี้เป็นด้วยความที่มันเป็น level สุดท้ายแล้วอันนี้มันจะชี้ไปที่ว่า page เราอยู่ตรงไหนอันเนี้ยมันจะชี้ไปที่ว่า page เราอยู่ IPTE 4 ตรงเนี้ยมันจะชี้ไปที่ว่า page เราอยู่ตรงไหนใน RAM นะครับอันนี้คือ page ของเราแล้วที่เราต้องไปหาเราเลยเรียกมันว่า physical page number แล้วก็เอาก้อนนี้มาเลยทั้งก้อนแล้วต่อไปด้วย page offset นั่นคือ physical address นะครับคำถามมีไหมAll right, so I know it's a lot to chew on. All right, so if you have follow-up questions, feel free to let me know. The first time ever that I learned about this thing, I'm confused. I was super confused as well. Afterward, it's really structured. Like basically, if you follow this pattern, you get the answer. It's like pretty structured, but look confusing in the beginning. Okay. With this, I can also extend this to 64 bits, which is your modern processor. Your modern processor break your address this way. The last 12 bits is offset. The other set of 9 bits, 9 bit, 9 bit, 9 bits, 9 bits, 9 bits are used to index into different table. That root that I told you, the root will tell you the location of the first table. The root is actually stored in the register. It's called the CR3 register, which you can set. This would show, basically the CR3 will point to the first table. Then you use the level 4 index to go into each of these level, right? Similar to the 2-level thing, right? And with the 64-bit, the status bits are they will be in the level 2 and level 1, basically the lower 2 level, which in this case will consist of the physical frame number, basically point to the next page table, and then some metadata used to track the status of that particular page. Then you use index level 1 to basically now go into the physical page number and the permission bit. Can I actually access the page? Right. Now that you have the physical page number, you plug the offset in, you get the physical address. Obviously, these tables are in DRAM, which means that to actually get your physical address, not even accessing your data, means that you have to go to DRAM multiple times. So that's a performance overhead. Let's say I have 4 levels for the page table. I have to go to DRAM 4 times, right? Just to know my physical address. So there are 2 problems. I cannot even access my data without knowing the physical address because they are in DRAM. I need the physical address for the location of my data, which means that one data access now turned into 4 access to the page table and 1 more access for your data. So that's 5 accesses. The second problem, you learn caching. Caching has a tag. The tag needs physical address, which means that I cannot even use the cache unless I have the physical address, which means that for every cache access, do I go to DRAM 4 times to get the physical address? If so, why do we even use the cache? Because that seems like a useless thing, right? But we are still using the cache because we actually can prevent a lot of this overhead, right? So to look into this issue and know how to fix it, I'll break this into each of the problem, right? So the first solution, again, I don't know where I want to access until I have the physical address. I have to go through the page table multiple times, and that's a slow thing. How can we prevent it? One quick idea is, what if we have a cache for virtual address? This is basically with as a cache for your virtual address. This will give you virtual address mapping to physical address in one step in the cache, right? We call this translation look-aside buffer. The idea is we don't cache the actual data. We have a separate cache just to store translation data, all right? And for commonly used pages, you would have the mapping saying, hey, this virtual page number mapped to this physical page number. This allows you to skip page walk, right? Because given an address, you can take the page offset, the rest are virtual page number. You use that to check, hey, is the virtual page number being cached? If yes, give me the physical page number, plug that into the page offset, we are done. We have the address. There can be multiple levels of the TLBs as well, kind of a smaller L1 private per core TLB, and then a larger L2 TLB. If the translation data is not in the TLB, that's when you have to do the page walk, all right? So you can also use large page, right? Because if you set 4 kilobyte page, it's going to be somewhat small. So TLB has limited size, right? Each entry in 4 kilobyte will cover just 4 kilobytes. So let's say you have 512 entry, the whole TLB will be able to cover just up to 2 megabytes, right? For example, here, you basically have 2 megabyte coverage. How many of your program use more than 2 megabytes memory? Quite a lot, right? With modern day application. So there are also ideas to make this page size bigger. So now one single entry might cover, say, for example, 2 megabytes, right? You can use the physical frame number in the second level with the longer page offset, which leaves us a huge page at 2 megabytes, right? And basically now modern OS also give you the option to adjust this. Some design, for example, GPU use a different page size. Some would use 64 kilobyte page size. Some will use a 16 kilobyte page size, depending on the generation, right? But when you use huge page, there's a trade-off. So your benefit is your TOB span wider area. So you are likely to be hitting in the TOB a lot more. You do page walk a lot less, right? But there are also key problems like fragmentation, which is basically, let's say you only need to use 10 bytes of data, but you are assigned 2 megabyte page, all right? The other 1 megabyte and 90 something kilobytes, you're not using them. So that's fragmentation and bloat. Memory bloat means that I actually use not all the memory I'm assigned, right? You can also have the page replacement problem, because now you basically cannot track the information in the smaller page level. You only see 2 megabyte range, and you don't know who to kick out. You can also have things like promotion, demotion. So on a plot here, right, as an actual experiment, running 3 VMs, and let's say the author from the paper OSCI 16 paper show that the 3 VM is being prioritized in a wrong way. It's not equal, right? VM3 get a lot of huge page. VM1 get some initial value and never get more. VM2 never get any, right? So that's also another problem. The thing is, with huge page, you also lose fidelity, lose control over small things. All right. To kind of compare this, like let's imagine a skyscraper, like a really tall building. This is like a Willis Tower in Chicago, right? So if you have a small page, like 4 kilobyte page, and your task is to clean this windows, right? What you would do is, well, if that window is dirty, so you would go and clean it, right? But if you have a large page, the problem is even though only one window pane is dirty, you don't know where, because you only have control over the big region. You only know that that whole site is dirty. So you would need to go and clean the whole thing because you don't have the small information. Right? So that's one of the downside with large page that are currently being investigated quite a bit in hardware and software. Right? I do have one paper on this. Actually, I have quite a few papers on like how to enable huge page for both the CPU and the GPU side, right? But if you're curious, let me know. The second solution, aside from the TLB, is what we call page walk cache. So what TLB is giving you, right? If you look at TLB, you get the shortcut from virtual page number to physical page number. You skip everything, right? The problem with the solution that skip the entire process is sometimes you will miss, right? Because you skip too far. Page walk cache comes in and say, hey, instead of skipping everything, so let's say your process page table, right? Another page table, another page table, another page table before you can get your physical address, right? And that's your income is coming in as a virtual address. What if you can have a cache that skip from here to here, or maybe from here to here, right? Or maybe from here to here. Skip a few levels. So that's a page walk cache. Given the virtual address, can I skip common path that I know that, okay, if this is this address, go there, right? So we call this a page walk cache. It give you much higher coverage, and you can now skip a few levels. So you can now cache partial translation data, right? So this is another really beneficial thing you can do. You can also use data cache to cache translation data. We're not going to dive deeper into this too much. Basically, use the data cache itself to be learned from the first slot of this lecture as cache for your translation, right? This is kind of like a last line of defense before you have to go to the main memory for the page table, okay? So these are basically to cache the page table location and the entry in there, okay? But overall, page walk is expensive. You would use combination of these three solutions to cache your translation data. There's many CPU side optimization from the year before 2000 to even now. In fact, right? I think I've told you that I'll be at a micro conference in this late October this month. Because I do have a paper on address translation, right? We try to come up with basically to give all the credit to the PhD student in Zurich, but basically he came up with the idea called Utopia that try to take advantage of different, I would say, application affinity at handling the basically virtual addressing using different structure. Right. If you're curious about this idea, let me know. But yeah, I work on this topic a lot. I do have a GPU side optimization as well. I also have the optimization over on the huge page problem I said earlier, the fidelity loss problem in PAC 2019. Also, I had paper on the GPU side here, micro and ASFOS, 17 and 18. We also have another design for the CPU in ISCA. A few years follow that. All right. So what you want to do is to reduce the overhead of translation, essentially, right? And now, so that's about how they get rid of the first problem. Address translation is really annoying, especially when you look at things like virtual machine. That's even worse, right? So we can dive deeper into that in a bit, if you will, right? But let's now talk about the second problem. Second problem is in many modern design, I cannot even go to the cache. The reason behind this is if you think about the index and the tag bit, all right? I have two options. I just said the cache use your address to index and tag, all right? I never said, is it a virtual address or a physical address? You have actually four options, right? The index bits in the cache can be from the physical address or virtual address. The same goes with the tag bit, which can be from physical address or virtual address. And here's the thing. Because virtual address is private to each program, there can be cases where you have program 1 and program 2, same VA, exactly the same virtual address. But they're actually mapping to different physical address 1, physical address 2, because they are different data. They're not the same, right? They're not the same. So VA go here, this VA go here, but it's the same virtual address. Here's the problem with some of these choices, right? If I use virtual address for the tag, this will be a problematic thing because I cannot tell you whether that block belongs to program 1 or program 2. So I cannot use virtual address as a tag. I can use virtual address as an index. That's okay. So every option for an index is okay because that just tells me the set. It doesn't really fully determine is that mine or not. Okay. What I just described earlier was a homonym problem where two programs have the same virtual address, but they're mapping to the two different locations. It's not the same data, right? And the tag needs to be able to tell the difference between the two. Otherwise, you're going to fetch the wrong data, all right? Let me say this in Thai again. ปัญหาก็คือว่าสมมุติผมมีโปรแกรม2โปรแกรมที่ไม่เกี่ยวกันเลยแต่โดยความซวยของผมเองมันดันได้ virtual address อันเดียวกันมา จาก2โปรแกรมอะ virtual address เดียวกันเพราะว่า virtual address มันเป็นอะไรก็ได้ที่ assign มาจาก OS ใช่ไหมครับแต่ว่าด้วยความที่มันเป็น2โปรแกรมอะมันแมปไปที่ physical address คนละที่กันก็คือ data คนละชิ้นกันเลยไม่เกี่ยวอะไรกันเลยใน cache เราจะมีพาร์ทที่เป็น index กับพาร์ทที่เป็น tag ถ้าผมใช้ virtual address เป็น tag ผมจะเจอ homonym problem ก็คือ virtual address เดียวกันมาจาก2โปรแกรมทั้งที่ data ไม่ใช่ data เดียวกันนะครับผมจะไม่สามารถเอา virtual address มาเป็น tag ได้ผมต้องการันตีว่าอย่างน้อยถ้าผมวิ่งไปที่ cache แล้วเจอ tag อันเนี้ยผมต้องรู้ให้ได้ว่าเป็น data ของโปรแกรมที่1หรือโปรแกรมที่2เพราะฉะนั้นผมต้องใช้ physical address เป็น tag เพราะ physical address ในกรณีเนี้ย homonym problem อันเนี้ยถึงแม้ virtual address จะเหมือนกันแต่ physical address จะไม่เหมือนกันผมจะแยกออกได้ด้วย physical address แต่ผมจะใช้ virtual address มาแยกไม่ออกเพราะฉะนั้นใน cache พาร์ทที่เป็น tag มันต้องมาจาก physical address โอเคนะครับพาร์ทที่เป็น tag ต้องมาจาก physical address You can also have the synonym problem where two different virtual address can map to the same physical address because they can be sharing between programs, right? I mean, to be honest, sharing between threads in the same program. The tag should be at least tell the difference between the two, otherwise you fetch the wrong data. So again, ultimately, make sure that your tag is physically tagged, right? So I just discussed the tag has to be from physical address. What about the index bit, right? With this 4, we said that homonym problem would kill this option and this option. So this is not possible, right? Now we have 2 more options, EIPT or VIPT. Now it comes to performance because to be honest, I don't care. The index bit can be from the virtual address and the physical address. It's okay. Both of them are okay. But here's the performance overhead, right? So if you think about it, issue with PIPT, use physical address for both the index and the tag. It means that the first thing I do, once I have virtual address, the first thing I do is to do translation to get the physical address, right? Then I use the physical address to index into the cache. Now I compare the tags. And then I use the tag to compare if this is my data, right? So you see, this is a sequential process. If I use the virtual address as the index bit, right, I would first use virtual address to index into my cache. This part would give me a bunch of tags, right? But then I need the physical address as a tag. So I use the same thing, right? But in parallel, I would use this for translation. So this becomes virtual address input. I get physical address as an output, right? Then I can use the 2 things to compare to get the data. So you see that this part, no, actually my bad. You see that this part 1 here is now overlap and handle in parallel. So this is faster. Top option is PIPT. This is PIPT. This is VIPT. So as you can see, VIPT is better here because you overlap the indexing into the cache with the translation. Right? So the issue with PIPT is sequentially done. These are slow, so you can basically use VIPT. Right? VIPT is actually kind of like a default policy. If you start to now read more papers in the last 5 to 10 years, they'll actually now propose and say, hey, maybe we use VIPT as a possible option or different mapping. And for these we just argued that we have enough DRAM, so why would the OS even keep the same virtual address in the first place, right? So maybe we will use EVIPT and avoid the case where it's the same virtual address. So that's another possibility as well from the research point of view. And it's a totally legit thought too, to be honest, right? So like, but the default textbook, at least for now, understanding of virtual memory, you would assume VIPT. Use virtual address for the index, physical address for the tag. Okay. The benefit is you can now overlap the cache lookup latency with the TOP lookup and still use the physical address for the tag checking. Okay. The downside is if the TOP missed, you still need to do a page walk, which is kind of a bummer. All right. You still need to rely on physical address. Now, last thing, I told you the last benefit of virtual memory is give you the illusion of a lot of basically a much larger DRAM, right? So page that are not used can be stored in storage. If you want to access them, we call it a page fault. The remedy is basically OS will spawn a thread to try to locate where's the faulting page in the hard drive, retrieve the data, give it back to your CPU. All right. You can also look at synonym problems where the two virtual address map to the same physical address, right? So possible location include things like limit the cache size, so the cache index is from the page offset. You can also search possible indices or do page coloring to guarantee that page from each process can go and ensure that the index of virtual address is going to equal the index of the physical address. The last benefit of virtual address is memory protection. I can utilize virtual address to check if my access is valid or not. If I have illegal access, it will tell you. Basically, the page table entry would contain permission bits, or earlier I called the status bit. These are permissions that allow you to check if the access is from a legit agent or entity that try to make the access. If not, generate an exception. Things like segfault is essentially from this permission check. These bits can include things like your address space ID bits, or the read-write, read-only bits, or the user supervisor bits. These allow you to protect your data from another application trying to access the address. All right. So to quickly recap on everything, right? So your day in life of a data access is you have the DRAM on the side, you have the caching structure and translation structure, caching at the top, translation at the bottom, right? The caching is like L1 cache, L2 cache, last level cache. Your processor has, let's say, a loading address, right? Let's say you do something even as simple as access array I. That's it. That's what you want to do. Just read that location, right? This is the virtual address. Basically, now you have the virtual address, and you want to basically locate where is the data. All right. So here's what happened. You would use the virtual address, the index bit, go into the L1 cache. At the same time, the virtual address will be used. You check the virtual page number, the address without the page offset, right? So virtual address will be broken down into the, again, virtual page number and the page offset, right? So you take this, check with the TLB. If it's a hit, you can use now, you now have the physical address. You use it as a tag bit, check into the L1 cache. Otherwise, if you don't have that in the TLB, you perform the page walk, which means you go to memory 4 times to get your physical address, which finally now you have the physical address, go back to the cache. Now you can access the cache. If it's in the L1, return the data back to this processor. If it's not, you go access L2. If not in L2, you go access last level cache. If it's there, return the data back. If it's not there, it's a miss. You now go and look at where is your data in DRAM and return the data back to your processor. That's a single load instruction, right? So now you can see why memory is a really important component, because these things take a long time, right? That's actually the wrap for, I believe today's lecture, right? So these structure in the middle is just to make sure data access is really, really fast, right? So that's the wrap. So let me end on this slide here, right? For this lecture, I think after the break, let's quickly talk a little bit about your project status and everything, right? I told you already I'll extend the deadline for lab 2. We discussed what day would work and what day would make sense for you guys. And then next week we'll come back and we'll talk about DRAM in detail. All right. Another. So I also took the liberty of like actually work with a lot of DRAM experts. So this is another topic I would like to share with you quite a bit. All right. So next week we'll talk a lot more about DRAM. I'll talk about a few research that my friends did, all right, on DRAM technology that are awesome, all right. And then I will continue on to kind of wrap up topic, move on to like a GPU, vector processor, multiprocessor, cache coherency. So these are kind of like an advanced topic in architecture. And then we'll follow with things like network on chip and RDMA. All right. Yeah, but that's it for today. Lecture part, Liz, I just want to stop the recording. Okay, then we continue with the discussion.